If we go back a couple lectures, we will remember that we first saw the fundamental theorem of calculus part 1 written in this form. And in English we said that that meant the derivative of an integral function is equal to the integrand as a function of the upper limit. And there were 3 asterisks written after that statement. I didn't talk about those asterisks then, but we're going to talk about what happens and why those asterisks are there in this lecture today. So, what's going to happen is this upper limit is not always going to be a x. There could be any variety of things written up there that are functions of x. And so the question is going to be, how do you then take the derivative of that type of integral function? And that's where we're going to use the fundamental theorem part 1 in association with something else we've seen before. Let's start with an example that we can do the long way and then see if there's a way we could have done it quicker. So here's a function g that's defined as an integral function. You'll notice that the upper limit of integration is not just x, it's x squared plus x. In other words, it's a function of x besides just x. And we're asked to find g primed. So in this case, I can do this the long way, which means I can actually find a formula for g and then take the derivative of g. So let's get rid of the integral and see what g of x is actually equal to. So fundamental theorem part 2 says I need an antiderivative of cosine t. So sine of t will do, and then I'm going to input these 2 limits of integration, one of which happens to be variable. So we get sine of x squared plus x minus the sine of 3, and that's what g of x is equal to. And so now we can do things the old way and just take the derivative of g at this stage where there's no integral involved. So what would g prime of x be? G prime of x is going to be the constant sine of 3 will just wipe itself out and become 0. Here I have a function that's really a composition of functions. So I take the derivative of the outer function. Derivative of sine is cosine. I leave the input alone, and then the chain rule tells me I have to multiply this by the derivative of the input, x squared plus x. And the derivative of x squared plus x is 2x plus 1. Our question here is, could I have jumped from this line to this line without doing this intermediate work? Okay, in other words, can I apply the fundamental theorem part 1? And the answer is yes. Okay, remember that said the derivative of an integral function is the integrand. Okay, here's the integrand as a function of the upper limit. So here's the integrand as a function of the upper limit, but you have to tack on this 2x plus 1. And what 2x plus 1 is the derivative of this upper limit of integration. So we're going to go back and amend things slightly. Fundamental theorem part 1 with the chain rule, okay, would look like this. The derivative of the integral from a to g of x of f of t dt is equal to the integrand, that's f, as a function of the upper limit, so f of g of x, times g prime of x. In English we'd say the derivative of an integral function is the integrand as a function of the upper limit times the derivative of the upper limit. So we're just adding on a little bit to what we had before. And I want you to notice that that doesn't really change what we had before. What we had before was the derivative of integral a to the x of a function f of t dt was equal to what? Well, before we said it's equal to f of x. If I want to apply this rule here, I still can, because I'd be multiplying that by what? The derivative of the upper limit. And the upper limit is x, and the derivative of x is just 1. So it's really happening. It really was happening before. We just didn't really talk about it because this was a 1, and it didn't really appear in our calculations. All right, let's do one quick example. Now that we know the shortcut, we're asked to find g prime of x for this function g. So g is an integral function, sort of. If I flip the limits here, it'll be an integral function. So I'm going to flip the limits and put a negative in front, because I need that upper limit to be the function and not the lower limit. And this could be done the long way as well. If you want to go ahead and verify that this is the correct answer when I'm done, that's cool too. Okay, now I want to jump from this line to the answer. So without doing things the long way, what is g prime of x? Okay, this negative is going to come down for the ride. The derivative of an integral is equal to the integrand, so that's 1 over t, as a function of the upper limit. So 1 over tan x times the derivative of tan x. And the derivative of tan x is secant squared x. So there's my final answer, and that could be simplified.